Welcome everyone, and thank you for joining me today. I'm excited to present our technical deck for AI engineering basics. Today's session is scheduled for about 20 minutes, and I'll be guiding you through the essentials of building AI foundations. We'll start with the basics for students and technical teams, then move towards more advanced engineering concepts. We'll also touch on large language models, or LLMs, which are a key part of modern AI. So, let's dive in and explore the fundamentals that will set the stage for your AI journey. Today, I want to focus on the core architecture behind modern language models, specifically the decoder-only approach that dominates today's generation tasks. This architecture relies heavily on components like multi-head attention, which allows the model to focus on different parts of the input simultaneously, and positional encodings, which help the model understand the order of words. We also have feed-forward layers and the add and norm steps, forming the classic attention is all you need structure that revolutionized the field. When it comes to training, we use the cross-entropy loss function, represented as L equals the negative sum of the log of the probability of the next word given the previous words. This setup is the foundation of our pre-training objective, training the model to predict the next token based on what came before. The key innovation here is the transformer architecture itself, introduced by Vaswani and colleagues in 2017. Self-attention enables us to process tokens in parallel, overcoming the sequential bottlenecks of RNNs, which significantly speeds up training and improves efficiency. Regarding scale, early models had around 1 billion parameters, but today, models like GPT-4 have grown to over 1 trillion parameters, with emergent abilities starting to appear at around 70 billion parameters and beyond. This massive scale allows the models to capture more complex patterns and knowledge. These models are trained on enormous amounts of text data, over 1 trillion tokens, using next token prediction, which is simply predicting the next word given the previous ones in a sequence. This autoregressive approach makes the model powerful for generating coherent and contextually relevant text. So, in essence, the foundational architecture of large language models is built on the transformer, with its attention mechanisms enabling scalability and efficiency, all trained on vast datasets to develop the impressive capabilities we see today. Now, let's look at how in-context learning's strength actually scales with prompt length. As we increase the amount of context we provide, models tend to perform better across different tasks. For example, in generation tasks like writing code, if we give a prompt such as Fibonacci Python, the model can generate the corresponding code, and we evaluate its accuracy using metrics like human eval. For question answering, providing a more detailed prompt, say, asking entropy definition, helps the model deliver precise and relevant answers, which we measure with metrics like F1 score or exact match. It's important to note that the more context we add, the better the model can perform, but there are limitations. One major challenge is hallucinations, where the model produces factually incorrect outputs. Additionally, the quadratic attention mechanism, which scales with the square of the prompt length, limits how long our prompts can be before performance degrades. Moving into multimodal capabilities, these models are also beginning to integrate vision and language, like clip-style models that handle image captioning or visual question answering. This opens up new possibilities for understanding and generating content across different modalities. We also use embeddings for natural language understanding tasks, such as named entity recognition or sentiment analysis. These models can handle zero-shot or few-shot learning, meaning they can adapt to new tasks with minimal example data. Finally, on the generation side, autoregressive decoding methods, like beam search or top-K and top-P sampling, are key. These techniques enable models to produce coherent outputs for tasks like code generation, summarization, or engaging dialogue systems. So overall, these technical capabilities showcase the impressive range of what large language models can do, from understanding complex language to generating high-quality content across various tasks. Let's delve into the different architectures and variants of large language models. First, when it comes to task-driven choices, we see that for generation tasks, models tend to use a decoder-only approach, like GPT, which is designed to predict the next token based on previous ones. On the other hand, for analysis tasks such as understanding and encoding information, encoder-only models like BERT are more suitable, since they process the entire input simultaneously. Attention masking is a crucial concept here. BERT employs bidirectional attention, meaning it can see all tokens in the input at once, enabling deep understanding of context. GPT, however, uses causal or masked attention, where it only sees previous tokens, making it ideal for autoregressive generation. Now, regarding the mixtral sparse experts, that's an example of a mixture of experts approach, which helps models scale efficiently by activating only a subset of parameters during inference. Instruction tuning, often involving reinforcement learning with human feedback, or RLHF, enhances model alignment with human preferences. When it comes to open source versus proprietary models, Mistral offers models under the Apache 2 license, making them accessible to the community, while some models are closed source, with proprietary APIs and weights, limiting access but often providing better control or performance. Moving on to how we access these models, there are different frameworks. For example, the Unified Text-to-Text framework, like T5 and BART, excels in tasks such as translation and summarization, where the model converts input text into output text, often evaluated with metrics like Rouge. T5 and BART are encoder-decoder, or sequence-to-sequence models, trained with masked language modeling, which makes them great for embedding tasks and classification benchmarks like Glue. BERT and RoBERTA fall into the encoder-only category, using masked self-attention to excel in understanding tasks and handling large contexts. Finally, GPT and Llama are decoder-only, autoregressive models, optimized for open-ended generation. Overall, the landscape of large language models is diverse, ranging from decoder-only to hybrid architectures, each suited for different applications and use cases. Let's take a look at the progression we see in deploying large language models. It starts with prompt-only usage, where you craft prompts to get the desired output. Then, moving to API integration allows for more scalable and efficient deployment, giving you access to powerful models without the heavy infrastructure. Next, for production environments, local fine-tuning becomes essential. This step lets you customize models further, improving accuracy and relevance for specific tasks. Throughout this process, attention mechanisms play a crucial role. They help models focus on important parts of input sequences, making responses more coherent and context-aware. On the implementation side, tools like Hugging Face pipelines make it easier to work with these models. Whether you're doing prompt engineering, applying quantization to reduce memory footprint, or fine-tuning with low-rank adaptation methods. Finally, integrating SDKs for chat completion, like OpenAI's, provides flexible parameter settings, such as temperature and max tokens, to optimize performance. All these steps, from prompt design to fine-tuning, are part of an engineering pathway that takes you from basic prompt use to fully customized, production-ready solutions. Let's dive into how we evaluate these models using Helm for a comprehensive assessment. Helm helps us compare different models across key performance metrics and strengths. For example, GPT-4o, with around 1.8 trillion parameters, is a proprietary leader excelling in reasoning and multimodal capabilities, but it doesn't offer open access. On the other hand, Llama 3.1, with 405 billion parameters, is open source, allowing for custom fine-tuning and boasting a strong 86% score on MMLU. Mistral, with 123 billion parameters, is also open and emphasizes edge deployment and speed, scoring 84% on MMLU. Then there's Claude 3.5, which isn't fully transparent about parameters, but is known for safety and handling long contexts, achieving 87% on MMLU. Gemini 2 offers a different approach with partial open access, supporting very large context windows like 1 million plus, making it ideal for retrieval augmented generation or RAG. Now, when it comes to deployment, we're looking at tools like LLM, which boosts throughput by 10 times, and AWS SageMaker, enabling scalable containerized inference. For example, Gemini 2 uses 123 billion parameters in a mixture of experts architecture for low-latency edge deployment, while Mistral's 405 billion parameters are friendly to fine-tuning, supporting up to 128K context windows. Llama 3.1 stands out as an open-source champion, integrating safety features like constitutional AI and supporting 200K context windows. And Claude 3.5 brings high scores in MMLU, multimodal capabilities, and reasoning, making it a leader in safety and performance. Looking ahead to 2026, we're expecting these industry leaders to evolve further, with production-level LLMs that push the boundaries of performance and deployment efficiency. The key takeaway here is that by using a hybrid open and closed approach, we can optimize ROI, balancing access, customization, speed, safety, and scalability to meet diverse industry needs. Now let's look at how we track our models using MLflow. Interestingly, MOE, or mixture of experts, can reduce the number of active parameters by roughly 80%, which is a significant efficiency gain. This helps us manage large models more effectively. Moving on to cost comparison, particularly between API usage and quantized inference. We find that once you reach around 50,000 or more queries per month, the break-even point favors hosting locally rather than via API, because inference costs tend to dominate in the long run. Next, let's talk about some key trade-offs and optimization techniques. For example, quantization can cut memory usage by up to 4 times and reduce VRAM requirements by 100 times. That's a game changer for deploying models on limited hardware. Then there's PEFT, or parameter-efficient fine-tuning, and LoRa, which can speed up inference by 2 to 5 times. Additionally, implementing KV cache can have the model size and boost performance by about 90%, making real-time applications more feasible. Distillation is another powerful optimization, helping us streamline models further. When combined with cloud GPU resources like the A100, which costs roughly $2 an hour, quantized inference can run at just a fraction of that, about 10 cents to $1 per million tokens for a 70 billion parameter model. For those who prefer self-hosting, token-based pricing models come into play. For instance, GPT-4o charges around $5 per million input tokens and $15 per million output tokens. But keep in mind, at high volumes, costs can scale quickly, so planning is essential. Finally, on the API pricing front, we see different models for inference, training, and efficiency. When we consider the economics of large language models, optimizing these costs is crucial for sustainable, scalable deployment. All right, let's wrap up with some key resources and takeaways. On this slide, you'll see references to the Hugging Face Hub, LLM documentation, and Q&A resources. These are great starting points for diving deeper. The next step I want to highlight is moving from simple prompting and API usage toward more advanced techniques like fine-tuning and retrieval augmented generation, or RAG, which are essential for building production-grade AI systems. The main takeaway here is that starting with prompting and APIs is a good initial approach, but for scalable and robust solutions, you'll want to progress to fine-tuning models or implementing RAG. This ensures your AI can handle complex tasks reliably. Looking ahead to 2026, we see some exciting trends. Ensemble methods will become more popular for improving efficiency, combining multiple models to get better results. The use of mixture of experts, or MOE, will continue to grow, enabling models to be both large and efficient. React loops will enhance multi-step reasoning, allowing models to think and plan over several interactions. Agents, integrated systems that combine various tools, will become more sophisticated, making AI more autonomous. We'll also see the integration of FAISS vector databases with LLMs, grounding responses in real data for higher accuracy. RAG techniques will further enhance model grounding and factual correctness. In terms of advanced techniques, expect smaller models like Phi-3 with 3.8 billion parameters and Gemma-2 to be more viable, especially for cost-effective solutions. Low latency and edge deployment will be driven by models like Llama 3.1 and Mistral, making AI more accessible in real-time scenarios. Privacy and custom fine-tuning will also be a focus, with proprietary models such as GPT-4o, Claude 3.5, and Gemini offering tailored solutions. And of course, high-quality, accurate responses will remain critical, so choosing the right model and strategies will depend on your specific needs. Finally, a decision framework will be essential, knowing when to use small models versus large, proprietary ones, or when to leverage fine-tuning versus prompting. It's all about selecting the right tools for the right tasks to build effective, production-grade AI systems.